Hello and welcome back to Steaming with Steve. Today we've got a bit of a different lesson where we're going to cover how integers work inside of your number systems. So let's jump on in. So first of all, I want you to have a go at writing your name in hexadecimal. So just pause the video here and have a look at the hexadecimal code and convert it. Awesome. So what you should have found for me is Steve. So I'm going to go across here. So 53, 54, 45, 56, and then 45. Or you could write the whole binary number instead of strings afterwards, which then would give you 8 times 5, so 40 little zeros and ones, if you saw the little binary thing at the back there. So there's a cool little video there. I'll put in the links down below. It talks about how cables and wires use those zeros and ones to convert. So first of all, what is a byte? Well, hopefully you've picked up before. A byte is 8 bits. So it's a whole series of zeros and ones, but there's only 8 of them in a row. So a byte was chosen for 8 bits because it's a power of 2, and it's a nice way of doing those groups. That's why previously we learned octal, because it allows you to sort of group those things as well. So 1 byte is representing a character in ASCII code, and then it gives you a range of numbers from 0 up to 255. So it gives you 256 different options by having those 8 bits all aligned. When we use 3 bytes, that represents an RGB value. So the red, the green, the blue, you use for 1 byte for each part of that. So then what is an integer? Well, that's just a whole number. So there's going to be 2 sets of numbers that we can look at this semester. So you're going to be looking at integers and then decimal numbers. So decimal numbers have the decimal point and allows you for solving rational numbers. Whereas when you're storing integer numbers, you're going to be dealing with whole exclusive numbers. So 42, for example, is an integer. So to give you a diagram of that, if we look at this is all the positive whole numbers, and then you can go to all the negative whole numbers as well, all the way up to infinity, and then down to negative infinity from that. Now, factorial is a really good way of showing how a computer can store this. So factorial basically means if you use the little exclamation mark next to a number, it means that number multiplied by all the numbers below it down to 1. So for example, 7 factorial is the same as 7 times 6 times 5 times 4 times 3 times 2 times 1. Now this allows you to show a really big number in a small way. That's what factorial allows you to do. So have a go now, pause the video. Wolfram Alpha's got the ability for you to type those in and see what you get. Cool, so what you should found is 3 factorial. If you did that, you got 6, so 3 times 2 times 1. 7 factorial, so 7 times 6 times 5 times 4 times 3 times 2 times 1. And then 18 factorial got a lot bigger quite quickly. So even though we've only added in another, the tens column, the number gets significantly bigger. Then 42, the number gets even bigger from there. So when you have 42 factorial, it's the same as 42 times 41 times 40, all the way down. Now they're really, really big numbers. And then you need to start considering whether or not your computer has a way of storing that size of number. So does a computer have unlimited memory? And the answer should be no. So it doesn't. So and you can't download more RAM, as much as controversial as that is, because there is no other options. So the way that integers are stored inside of computers, generally what happens is there's a set of bytes that are attached, so either 2 or 4 bytes, depending on the programming language. And you need to remember your powers of 2. So what we have for the first byte and then we have the second byte is you basically have 16 separate containers that can store the 0 or the 1. So from that, we could, I've put all the powers of 2 there so you can see it. So if we had the number 101010, that would mean you have 32 plus 8 plus 2, which if you add all those together, you get 42. So that's the binary representation of the decimal number 42 when we store that inside the computer, which carries on from what we've done before. So then how many bytes would you need to store how many degrees there are in a circle? Just pause the video. And hopefully you would work out, again, you still need the 2 bytes. So when the degrees in a circle, you still need to count in powers of 2, and you would go from 0 up to 359 degrees in the circle. So and then this would need at least 2 bytes. So even though you would only go up to this section here with 2 to the power of 8, you still need to include that extra byte. So then how do we represent negative integers in binary? Well, there's a couple of ways, but the main one that most people use is signed integers. Now, there's a couple of ways of doing signed integers, and we'll unpackage that. But I'm going to show you the simplest way of remembering it, which is this. So signed integers, basically they're the same as normal integers, except the first bit on the left represents if it's positive or negative. So 0 means that the number is positive, whereas 1 means it's negative. So if you have 8 bits, that first bit there represents if it's positive or negative, and then everything else is just the size, or what we call the modulus. So the remaining bits that are left over is the modulus, which then gives you how big the number is. And then if it's negative, this is where it gets a little bit different. You start from the backwards. So you work backwards with the largest number possible, and then go from there. So for an 8-bit signed number, basically the positive bit is this. That tells you if it's positive or negative. And then everything else after that tells you the size of the number. Now this is a little bit reversed for some signed integers. So some people will teach signed integers where it's just that bit and then everything else stays the same. I'm going to get you in the mindset of how the signed integers can work, but you're basically going to learn a more advanced concept, which basically means you work in reverse like that last point there says. So these are all the modulus bits on the end. And then that equals 53. So when you're mapping it, what happens is, as soon as you say it's signed or unsigned, it effectively halves your options. So if it's unsigned, you can go, if with a 4-bit number, you can go from 0 all the way up to 15. If you make it signed, you go from 0 up to 7, exactly the same as before, except now, if it's 1, 0, 0, 0, that's the smallest number that you can make, which would be -8. And then that works all the way back up to -7, -5, -4, -3, -2, -1, and we go from that. So notice the positive values include the 0, and then the negative values will always shave one more off the end. So your turn, draw a table for signed versus unsigned for 3 bits. So if we had the 3 bits there, you should have got something like that. So notice that with the 3 bits, you go from 0 up to 7. You can go 0, 1, 2, 3, same as normal. But now, when we get to the 100, it becomes -4, -3, -2, and -1. Now, some people will teach the other way around, where you'll just go 1, 0, 0 is the same as -0, and then -1, -2, and then -3, which then it adds another layer of complexity. But this is a nice way of seeing how unsigned works. So unsigned and then signed, basically what happens is, if it's unsigned, it does all these positive numbers, so 0 up to 255, but then as soon as it becomes signed, you have to go then down to -128 up to 127. Notice that we don't do -0 with this particular method. So positive values are exactly the same when looking at both unsigned and signed. Notice that the -1 always represents with all the bits set to 1, and when counting in reverse, you get the minimum value, which is -128. So the negative value is always 1 bigger than the positive value in terms of its modulus. The smallest value will always start at 1 and go up to the modulus values all set to 0 as well. So integer ranges, if you have 1 byte, you can go from 0 up to 255 like we've just explored, and then as you add bytes, it gets a lot bigger. So 2 bytes can go up to 65,000 unsigned and have the range halfway between those two, all the way up to 8 bytes, which then gives you a monster of a number, right? So by adding more bytes, increases the capacity of the language to store how many bits are used. So how do you add in binary? Well, it's pretty simple. Basically, add the columns together. If there's an excess, you carry the 1 to the next column, and then repeat until all the columns have been completed. So in this little simple example here, 7 plus 5 gives you 12, so 2 carry the 1. 1 plus 1 gives you 2, so you get 22. Then if we try that again in binary, we need to know the rules first. So the rules of binary addition, it's really awesome. You only need to know 4 things. So 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and then the only thing that's a little bit confusing is 1 plus 1 equals 10, because 1 plus 1 in binary is 2, but we represent the 10 in that binary notation. Cool, so we put that off to the side, and then there's a little video there that you can watch if you need as backup, but this should be pretty clear. So if we go 1 plus 1, you get 0, carry the 1. 1 plus 0 plus 1 gives you 0, carry the 1. 1 plus 1 gives you 1, 0. Now, that might look a little bit confusing, but if we change those into decimal numbers, 1 plus 101 is the same as 5, and then this is the same as 5 plus 3, which then gives us 8. which is pretty cool. So does 5 plus 3 equal 8? Absolutely. So we're all good. So just pause the video, grab a bit of paper, and have a go at these. Awesome. So what you should have found, 11 plus 10 gave you 101. 100, number 2 gave you 1100. Number 3 gave you 1101. Number 4 gave you 1110. Number 5 gave you 10,111. Number 6 gave you 10,100. Number 7 gave you 11,001. Number 8 gave you 10,000. Number 9 gave you 1,110. Number 10 gave you 1,110. Number 11 gave you 111,001. Number 12 gave you 111,110. Number 13 gave you 1,001. Number 14 gave you 10,110,111. Number 15 gave you 10,110,110. And then number 16 gave you 10,100,111. You can, and that was a lot of words, sorry. You can also add 3 numbers, so you can have 1,101 plus 1,110, 1,101 plus 110 plus 111. So what happens is exactly the same, you just follow the columns. So 1 plus 1 gave you 10, so you put a 0, carry the 1. 1 plus 1 plus 1 isn't 3, it's actually 11 in binary, so you put a 1 down the bottom, carry the 1. 1 plus 1 plus 1 is actually 4 in binary, so we put the 0 there, then carry the 10, and then 10 plus 1 gave us 110. Pretty cool. And then if you want to change them into binary, as from binary into decimal, just to back up, you do 13 plus 6 plus 7 is equal to 26. Have a pause of the video, see if you can do that one. Cool. So what you should have found is 1 plus 1 plus 1 gave you 11, so 1 carry the 1. 1 plus 1 plus 1 gave you 100, so put a 0, carry the 10. 10 plus 1 gave you 11, so 1 carry the 10, and then 1 plus 10 gave you 10. And then that's what it would look like. Notice with the Nessa criteria, if you show some understanding and show some of your working and it's wrong, you still get 1 mark. If you don't show any working, you put the wrong answer, this is my huge advice, you will get 0. So if you put 11101, you would get 0 if you didn't show your working. So please, like all good maths teachers, make sure you do your working. Have a go at the binary worksheet. That's it for me. Hopefully that's given you some insight. If you have any questions, please put them in the comments down below. I'll try and answer them as well. Thanks very much. See you next time on Steam with Steve. Adios.